Vector space theorem on basis statement. First we are going to write a statement. Let V be a n dimensional vector space, then any subset of V, any subset of V with n elements which span V is a basis. So what is given here? The given, I'm writing here, given dimension of vector space V is equal to n. The first thing we know is that dimension of V is equal to n, and suppose S is equal to, S contain n, S be any subset of V with n elements, say V1 bar, V2 bar, Vn bar, any subset of V which span V, that is ls is equal to V. And what is our claim here? Our claim is that set yes is a basis set. Now to prove basis, we want to show that it is a span and linearly independent, but already it is given span. So to prove that set yes basis for vector space V, we want to show that set yes is linearly independent. Why only linearly independent? Because already it is given span. So there are two conditions to show basis. When we said it is a basis, if it is a linearly independent plus a span, then we can show that we can say that given set S is linearly set S is basis. So prove by using contradiction. Suppose prove by using contradiction. That is, we assume here that is, suppose set S is linearly dependent, not independent. So what this implies? So by using definition of dependent, this implies there exists at least one vector from S which is linear combination of other vectors from S. Okay. Yes. Now let S dash be a new set. This S dash be a set. S dash be a set obtained from obtained from S by deleting this vector, that is this dependent vector. Okay, so we remove this vector, dependent vector, and this implies set S dash contain n minus 1 vectors, again which span V. It doesn't if we remove the dependent vector, it does not affect our spanning. Okay, so span V. Now if S dash is again not dependent, again dependent, say it is dependent, and then there exists again a vector, at least one vector which span one vector if in set S, which is linear combination of vector in S. So again let S double dash be the set obtained from S double dash by deleting this vector, and which vector? This dependent vector. Okay, so continue this process. And what is the here? S double dash, set S double dash contain n minus 2 vectors, and which span V. If we remove a dependent vector, it does not affect spanning, so it's span V. So if we continue this process, finally we obtain set, say S star which span V and contain S star V, and which is linearly independent and contain less than n vectors. But this implies dimension of V is equal to this implies dimension of V is less than n, and which is contradiction. This is what? A contradiction. What is a contradiction? Because what is given here, you can see here, I am highlighting given here. What is given? Dimension of V is equal to what? N. But here we obtain dimension of V is less than n. Why we obtain this? Because we assume contradiction, and therefore which is contradiction that dimension of V, set V, vector space V is equal to what? N. And therefore why we obtain such a contradiction? Because we assume here wrong, where I am highlighting again. Okay, here, so what we assume here, suppose S is what? Linearly dependent. Here we assume wrong, and that's why we obtain here some contradiction. And therefore from this what we can say, that set S is linearly independent. But this implies, since S is a span, set S is span and independent and linearly independent span, it is already given in statement. This implies set S is basis for vector space V, hence the proof.